So welcome back to COMP526 and to Unit 3. We'll talk about efficient sorting, in particular, sorting lists of things as fast as possible on a computer. There's quite a few learning outcomes for this one. But these are just spelling out many little things. So we'll talk about merge sort and quick sort because these are the efficient sorting methods for sequential and in-memory. And I think it's worthwhile for you to know the performance characteristics of these. Then we'll briefly talk about the single lower bound where you usually touch base on in undergrad classes, this comparison-based lower bound for sorting. And we'll see how to beat it. Then I added a new section about adaptive sorting. And we'll talk about parallel computation. First in the context of sorting and later also in the context of other problems. So how can you make use of all the multi-core machines that we have? Here's an overview in terms of the topics. And we'll go through those one by one. So they parallel the outcomes. I don't think I want to repeat myself. I want to motivate very briefly before we start why we should study sorting in the first place. One fact that I'm not sure you are aware of, it's an unsolved problem to a certain degree. Even though every programming language comes with a sorting implementation and sorting is generally fast, I mean, it's not a big problem if you need to sort your data first. You can usually do that in a reasonable time. If you want to look very closely from a more eternal truths perspective, what is the best possible sorting algorithm? That would be one that has the minimal number of comparisons, and that's still an open problem. Last progress on this is from the 1950s. Small bits and pieces have been added to this, but the fundamental algorithm that's best possible in this sense that we know is 70 years old. That's maybe surprising. At least I always find this kind of cool. Sorting, of course, is a building block for many other tasks. So if you can sort fast, then other tasks inherit that speed. It's often convenient to pre-process data that way, or it's just part of a bigger algorithm. For example, many algorithms that work with multidimensional data, they start by sorting data according to one dimension and then work from there. And so, and they do this multiple times. Apart from that, it's a nice playground to test out some of the theories. It's of manageable complexity in many ways. After all, it's just bringing a list into order. That's a problem you can explain to primary school kids. But then applying the more advanced techniques to make this really fast on a computer is still active research. All right. I want to focus first on some classic methods that some of you will have seen. And for others, I'll go through them quickly so that you have all seen the same version of them, at least. I will briefly talk about some personal pet project of mine, but also beyond that, how to exploit it if your list is already somewhat ordered, and then the big topic about parallel computation. For the first part, I want to make sure we know the rules of the game, as I called them here. And this is also setting up the notation for the algorithms that appear on the slides. So we start with an array of objects. And again, in Python, you don't really have arrays, so it would be a list. For all intents and purposes, you know from Unit 2, Python lists are still arrays, even though resizable ones. But the important part is we have an array where we can access the ith element for any I in constant time, and we can overwrite it. What we cannot do is insert something into the middle of the array, because that would really mean copying many elements over. All right. The second assumption, if we want to sort objects, we want to be as general as possible. So I don't want to say we're specifically just sorting integers. Not at this point. We want to sort arbitrary objects. And what I need for that is, if I give you two objects, you tell me which one is smaller. And you can decide what smaller means for you. It's in libraries or in programming languages, there's different ways to do this. In Python, you can sort objects of a certain class. And there's a way to overload this built-in operator, less or lesser equal, by implementing this function, which obviously stands for less than. So I guess it's the strictly less. And in Java, there's an interface called comparable that has this method, which again allows you, given two objects, decide which one is smaller. Okay. So this is something that all programming languages and libraries allow you to do. You give it a list of objects, and you also tell the sorting method how to compare objects. We'll usually think about sorting in place. So we're given the array and we modify the input. That's why it says rearrange or permute the given elements. And well, of course, at the end, it should be sorted, which means for us, the smallest element is on the left, and then they increase. So it's ascendingly sorted. For the first part, we assume that the array fits into main memory. That's an important assumption, because it means that different algorithms are efficient. And we use just a single processor, but we'll come back to that at the end. The rules of the game good so far? I wanted to ask you to also guide me how quick I want to run through this, what you've seen about sorting and the theoretical side of it. So the question is about the complexity of sorting, and take it as you think this is meant when I say complexity. It's not necessarily completely well defined. Can I show this picture in big? I don't know where this picture is shown at all. Just ignore it. Set up as a free text answer anyways. Okay, I'm confused by Slido, but here's, if you want, you can pick one from the list. Try to be as precise as possible, though. Do we need another minute? That's not the question. It's the question, what is the complexity of the sorting problem? I'll explain what I mean by that. But the question's well defined as is in my definitions. Anyone still busy? See a few people typing. Let me show answers. So there's a big blob for this one, and in a sense, that's almost correct. Let me very briefly remark on the question. So this is a bit of an aside and not the main focus for this module. We'll mostly be talking about concrete algorithms and how good they do, how well they do. But you can ask about the complexity of a problem. In this case, the general problem of sorting a list. And then what people mean by this is, first of all, in the worst case is usually the assumption, and asymptotically for large n as usual, and ignoring constant factors as usual. So we're talking about theta classes. Now, the complexity of a problem, there are two sides of it. There's a lower bound. How good can it possibly be solved? What's the fastest conceivable method for sorting? And there's upper bounds. These are algorithms, concrete solutions that have a certain running time. Ideally, in the eternal truths world, we can find some things that match here. So we know a lower bound and an upper bound, and they're in the same theta class. Then we can say the complexity of the problem is solved and is theta of whatever it is. Okay. Now for sorting, we're actually in the situation of being able to say that. It's theta n log n. If you define sorting to be comparison-based sorting. We'll cover this in more detail. Because you can't see this in this Wordle picture, there were 8 votes for order n log n for this big one, which looks much bigger, than 8 out of 54, if you ask me. There's 5 more votes for theta of n log n, and then there's votes for the answers, and I don't remember which one was which. So G got another 5, and H is this one, got 3, and where's theta n log n I? Not so many votes for I, it seems, further down the list. Can't find it. No one voted I? Seems so. Okay, yeah. So don't worry, this is just out of interest. I think questions of this type are useful to have in mind, but I take it that not so many of you have seen the question formulated in this way. Yeah, so we'll touch in this module on both sides, both the lower bound and the upper bound. And this is one of the lucky cases where we can completely settle the complexity of the problem. And that's where the theoretician says, oh, job done, I'm going home. From a practical side of things, this is sometimes not the end of the story, because it leaves open whether the constant factors are the same in the lower bound and the upper bound, or even if any of the algorithms that we have has a reasonable constant factor so that it is useful in practice. And it sometimes leaves open other things, like is this only a problem in the worst case? And if we relax that a bit, we can improve the algorithms. So from our perspective, where we take a look at, yes, eternal truths, but also things that are useful and effective in practice, we'll not stop at saying n log n is the answer.